three-dimensional object. In this material can be deposited, joined or solidified under computer control. The first patent that exists from this is the liquid metal recorder patented by Jonas F. Gottwald in year 1971. In the early 1980s, this method was thought to be suitable only for the production of aesthetic prototype. Now it has been evolved into a lot more since then. As of now, 3D printing has successfully made its way into manufacturing, medical, industrial, and socio-cultural sectors. The thing that make it attractive is its availability to produce very complex shapes with reduced weight, apart from many other advantages. It has been very handy in the time of this pandemic. It is indeed a very up and coming topic that has attracted the interest of many industries, making it imperative to develop our knowledge of this subject. Nearly 500 participants registered for this FDP, but due to certain constraint, we approved 200 participants. I hope this FDP will be beneficial for you. With this, we would like to commence with our session. I hand over mic to Mayank for further smooth conduction of the FDP. Mayank.
Yeah. Okay. Thank you, sir. I would like to inform you all the candidates or the participants. Please watch this full session of all the guests, because we have made perfectly blend of 3D printing from the scratch to a level from which you can or anybody can start their own venture. So I would like to invite Dr. C.P. Paul, sir, to start your session, sir. Over to you, Paul, sir.
Good morning, everybody. This is Dr. C.P. Paul from RRCAT. Are you able to hear me?
Yes, sir.
Okay, fine. So we are going to just a minute. Yeah. Let me share the screen, then I will start the. Are you able to see the screen now?
Yes, sir. Screen is visible, sir. Fine.
Okay, let's start. So good morning, everybody. This is Dr. C.P. Paul from Raja Ramanna Center for Advanced Technology. Today, in fact, it's my privilege to be with you. And when we talk of the ongoing pandemic all around the globe, there has been a discussion that so many things have pushed down and things are not coming to the state. But there are many things which is happening in extraordinary way. And one of these things is FDPs and other workshops, which are paving a way for us to learn and grow and share our knowledge. So many things are happening. And one more advantage is, since we are using the digital platform, it is providing opportunity for many of us to present our things and share our knowledge, not once in a month, but maybe many times in a month. So this is also a good thing. So with this, I will start my presentation. As suggested, the title is Introduction to 3D Printing and Design. As the FDP title is also 3D Printing and Design. Let's have a short introduction, how the things are being done, and we'll try to understand. So let me start with my parent organization. RRCAT is a premier R&D institute under Department of Atomic Energy, Government of India, engaged in non-nuclear frontline research area of lasers, particle accelerators, and related technology. This is also a CI of Constituent Institute of Homi Bhabha National Institute, a deemed to be university under Department of Atomic Energy. So if we talk of this, we have total 1570 employees. We have 45 external PhD students and almost same departmental. So we have about 100 PhDs. We gather about 150 MTech students every year for the project work. With this, now issue is, how can you join our RRCAT? There are 4-5 way methods you can get associated with RRCAT. Number one, you can join as a scientific officer through BRC training school. through OCS, or BRC online program. If you are PhD, you can join with the K.S. Krishna Research Associateship. And we also have PhD program under HBNI. Those people who doesn't know about the HBNI, I will just share this. Homi Bhabha National Institute is one of the fast growing university in the country. It is ranked 16th in NIRF ranking. And this has been in Nature has mentioned that this is one of the promising university which is globally growing up in a very fast way. So we have just spent some 12 years as HBNI, and you see so many things happen. Rank has come up very nicely. Now we also organize OCAL program, orientation course on the accelerator lasers and related science and technology program. This is specifically for the students who are in the final year of their BTech or doing their master's program. So this is for them. They can come work and understand in 2 months, and after that they can pursue, if they can know about how and what the research career is about. I'll also start with my lab. What are we doing is actually I'm heading a laser additive manufacturing program, and what are we doing? We are starting from system design and development to the material processing, material testing, qualification, validation, and multi-phases modeling. Means it's not only that we procured machines from abroad or some foreign machines and we are trying to do this. No, it's not the case. RRCAT has developed its own machines, and we are having for metal additive manufacturing, and we are pioneer and the leading in this area. If you talk about the team, we are pretty, 16 people. You can see 16 people team, and these are the permanent employees. Then we have 5 PhD scholars plus 3 MTech scholars. So pretty balanced team, and all are working for the laser additive manufacturing program at RRCAT. So let me come to the presentation plan. The presentation plan is, we'll start with the introduction. We'll be talking of additive manufacturing and conventional manufacturing comparison. Then we'll be saying why do we need and what are the advantage and limitation of this, how EM evolved, what are the steps. We'll be talking about the classification, and finally I'll come to what our experience is about laser additive manufacturing. Whatever content I'm talking today is the part of these 3 books. One is Laser in Manufacturing by Professor J. Paulo Davim. Another is Additive Manufacturing Applications and Innovations. This is edited by Rupinder Singh and J. Paulo Davim. And third book that we are working on it is already in the press, and which is likely to come and release in April 2021. And its name is Additive Manufacturing Principal Technologies and Applications. So this is the thing which is going to come. And what I want to say is that whatever is being taught in the area of additive manufacturing, whatever the AICD syllabus is, everything will be covered in the textbook that we are writing, and it is under press. So let me start. You all know that conventionally the materials are made by subtractive process. The process which are contributing to this are deformation, casting, joining. So this is the basic thing. What happened in 1987? People thought of changing this sign from minus to plus. And what happened? This minus to plus sign, change in the sign, made a shop floor job to a designer job into a air-conditioned room. So this is the big change, and this brought a lot of revolutions and thinking, and changed the very thought of doing the job in the industry. So what it is, and there is one full-fledged standard which is called ISO ASTM 52900. This defines process of joining materials to make parts from 3D model data layer by layer, as opposed to the subtractive manufacturing and formatting manufacturing technology. Now, what happens if you see this definition? There are 5 sentences that qualifies any process to be called additive manufacturing. Number 1, it should be process of joining of material. Means it should be joining the material. You cannot just do the subtractive another operation if you are talking of additive manufacturing. So it should be joining of the material. Second point is it should always start from a 3D model, so that then you build upon. So that is another requirement. Third is it should be layer by layer built up. You cannot have just something starting from somewhere and then just finishing. You are not doing layer by layer operation. So that is also compulsory here. Then fourth is it should not be a subtractive methodology, and it should not be a formative methodology. So these are the 5 criteria as per this definition, which defines a process to be called additive manufacturing. There's so many processes. See, conventionally, you see, we may be thinking, for example, I see there is a big chart, and you see I have put down what are the processes being qualified and why they are not qualified. So you see, NN means they are not qualifying all these points, and they are qualifying limited points. So let me explain you with one or two examples. So you talk of centrifugal casting. Centrifugal casting can make you pipe of any diameter. We all know that. Just by changing the by changing the centrifuge speed, you can have a variable thickness. But issue is, can we have any other shape rather than a cylindrical? So we'll say no. So what happens is this process gets disqualified. Similarly, if we talk of forging, is it it is not a substitute, it's qualifying, but can you start with the joining of the material? No, forging doesn't do it. Does it start with the 3D model data? No, it doesn't start. Is it a layer by layer process? It doesn't. And is it a formative process? No. So what is happening, you see, we have to put all the 5 criteria for any process to be called additive manufacturing. And if it is not doing, it may look very close. For example, now take off conventional welding. I'm talking of 3D welding. I'm talking of conventional welding. So in conventional welding, we are joining the material. Yes, we are joining. Are we starting with the 3D model? No, we are not starting with the 3D model. We are just taking the torch and starting building. Is it a layer by layer? No, we are joining two plates. So it's not. Is it a substitute protein? Yes, it is. It is not a substitute method. Is it not a formative? Yes, it is not. But again, these 2 criteria, it fails. So these are the points which need to be considered whenever we are talking of any process to be qualified as additive manufacturing. There are many names to this process. You see, all goes to AM. Maybe 3D printing, rapid prototyping, additive fabrication. So many names. So I'm not going to detail of this. In fact, AM is not a new concept. It existed since long. You see, a seed grows into the plant. Similarly, a small infant grows to the adult. In everything you see, they are taking something in. Things are not being removed. It's not like they are a big bulk and then it's cut and given the shape. No, it's additive. Similarly, so what I want to say is additive is a more natural way of growth. It's not like if you want to make something, so it's a nature way of growth. Similarly, people try to do something in this direction. If you construct a house, you can see you can take some shapeless things and just keep on growing and layer by layer. So it is very close to it, but still it is not additive, but it is close to that. Now, major problem is why people didn't do earlier, because what is happening, we never had that much resources. We didn't have control on the process to start in this way. Today, as the technology grew up, some of the things have come up and things are changing now. This is a quick comparison of additive, subtractive, and formative. I'll just see some of the things. For example, in terms of dimensional accuracy, additive was low to medium, subtractive good, very good dimensional accuracy, formative as medium. So what is happening, if you want to have very good precision and dimensional accuracy in your job, then additive is not solution as on today. If we talk of surface finish, you can see here also it is disadvantageous. But if you talk of the complex geometry, for example, you want to make a very complex geometry, then AM is one of the very good potential solutions. And subtractive has got limitations, because if it is a 3-axis machine, you know that limitation of 3-axis. If it is 5-axis, you can do something, but still there are issues. So that is, and formative, yes, definitely medium sort of scale you can give for it. So these are this in terms of green technology. AM has got reduced material wastage, subtractive has got high material wastage, and formative is there, but it is not to that level, but still it's fun. So this is the comparison, quick comparison of these 2 processes and different head. You can have these ideas and go ahead with. Now, if you talk of the cost per part, what is happening with additive manufacturing? In additive manufacturing, the cost is not going down as the number of part grows. So what is happening? Whenever it comes to the customization, comes to the limited production, additive is going to be a very good, because the cost per part will be less. But in case of the process, when you need thousands and hundreds of thousands, then substitute and formatives are going to lead the way, and that is the thing which is being practiced globally Now, how did the additive manufacturing started? The concept, though, came in 1987 in full-fledged, but prior to it, some of the things were done earlier. For example, one of the concept, if you see in USPTO website, US Patent and Trademark Office, in this website, you read when photo sculpture is mentioned, you see what the guy did is to make a photo. What that fellow did is he made something like this and then rotated and tried to establish using this partition things, and which allowed him to do it quickly, and then he patent for it in 1937 or maybe 1980. In 1892, they wanted to make some topology of the land, topography of the land. So what they did is they did some measurement, and after that they made a layer by layer things so that people know that where is the hill, where is the cavity, where is the die, what is the taper and all. So some small scale down model topography they did. So like that, small things were done, and people are trying to make it, but it was never into the scale that today it is, and it was introduced in 1987. After introduction from 87, if you see, it has got really big growth. And what happened is, when we were slowly things started coming up, new technology joined in, and now what is the projection? The projection is by 2032, people are expecting full body organs to be built by additive manufacturing. Means, if you have your, kidney went bad, people are thinking that the kidney can be built using the method and it can be replaced. So we need not to hunt for this. That is the expectation people have. Slowly things are growing in that direction. What is the methodology? So much we talked about. So methodology is like we start with the pre-processing. See what is happening in additive manufacturing. People understand that it is very simple to go ahead with. It's one stage, but it's not so. There are so many things, so many points we need to consider to go ahead and work with. For example, I'll tell you, if you talk of overall methodology, it has got 3 steps. One is pre-processing. In pre-processing, we talk of concept generation and design. You have some concept. You have to, work for this, make it mature. You have to bring to the level so that it becomes a really good one to work with. And this concept can be started from a CAD model, or you can have a 3D scanner to scan and get it done, or you can use some computer-aided engineering software, for example, ANSYS or others, to have the idea and get the idea of it. So finally, you start making the model. Once you made the model, we are talking of the customization of this design. See, we think of it how this design can be adopted in the manufacturing and in the real life. For that, people put more risk, and then they talk of conversion these particular model into the machine specific format. Then we plan to how should we orient, because wrong orientation will lead to many other issues. For example, in most of the machines, when we build layer by layer, along the z-axis strength comes out to be lower, while in x and y plane it comes out to very nice. So what is happening? If you want more strength, you should build your component in such a way that your loading axis should be either in x or y or combination of it, and z should be discouraged. This is just thumb rule, but there are ways people are trying to fix this problem and doing it, but this is just something I wanted to share with you. Similarly, at the third stage, people talk of the machine setup. People talk of what is the layer thickness they are talking of, what should be the rasting pattern, how, because rasting pattern, how should you fill the area. When you use some standard software, for example, you talk of Cura or you talk of Simplify 3D or some other softwares, they have some standard pattern, but what is happening for the polymers, the rasting pattern doesn't make a lot of difference. But in case of metals, ceramics, this is going to make a big of change. So therefore, one has to really work and focus on it. What should be the rasting pattern? All this additive manufacturing, wherever you want to have an inbuilt cavity, we need to have some support structure generation, and how this supports. So all these things are the part of the pre-processing. People have to give a thought on it. It can be done by software or it can be by the designer, but somebody has to do it. Once this is done, it goes to the processing stage. Then we put the machine setting, we go for the selection of the process parameter. We have some closed loop control to see how the things are being done, or change the documentation of, we can, people are talking of using artificial intelligence and many other concepts, machine learning, so things can be done in very better way. But again, this is not regular in the field. There are a couple of things which is happening, and people are trying to work on the processing side. Once this processing side, when processing is done, the component is ready, then we have to think of post-processing. See what is happening, I said you, we have already put some supporting structure here, but supporting structure is not a part of the component. We have to remove this, remove the support structure, or maybe some finishing operation. If it is a metal, then what is happening? We know that during the deposition, some distortion has come, or the microstructures are different. Can we change these and fix them? So that sort of post-processing things are to be planned and done. When all these things are done and desired property is achieved, it is the final product. So this is the general and overall methodology of additive manufacturing, and one has to understand and just getting a model, printing on a machine is not the 3D printing. You have to think constructively, focusedly, and overall method. That is the thing that I want to emphasize on. Now it shows why additive manufacturing is important as on today. Now, I always show this product value addition smile curve. This is one of the things that we have to understand. You see, in the industry, there may be many departments. The departments are shown in the x-axis. For example, the department can be R&D, design, logistics, inbound logistics, manufacturing, outbound logistics, marketing, after sales, and services. Now, in 60s and 70s, the manufacturing people were getting a bit less salary, but the difference between the R&D guys and this was not much. It was there, but it was not much. But today, what happened because of the automation and many other things, the manufacturing things are getting down and down. The salaries are paid less, and the value addition considered by them is also very less. They say everything is now standardized. Only you need somebody to supervise the stuff. Why to make sure? But on the other way, the people at the R&D level or after sales services, they have to do a lot of things. So a lot of value addition is done by them to the organization, and they are paid compensated accordingly. So this is a big difference that we have seen in these years. Now, what we have to do as a person who is working in the manufacturing area, if we just focus on this, tomorrow we may not be important for the organization, and organization may ask us to leave. Now, what to do? The best thing is if we can take some of this area or this side area, so that things can be the relevance of the people in the manufacturing can be established in this. So what we have to do as the people working on it and students who are to whom we are teaching, we should inculcate these things, that they are not going to stick to only to manufacturing or some supervisory role, but they have to also think of some other domain so that they become relevant to the organization and they can continue this. So now let me come back to the next stage, what we talk of why additive manufacturing. Whenever we talk of additive manufacturing, this is a pretty old slide I had been using for maybe more than 5 years. And this is a fantastic example how additive manufacturing needs to be done and work on it. See, first point that I always emphasize is now today there is a cutthroat competition. When I talk of the cutthroat competition, this is just because of the more players, more models, and reduced volume per product. How it is working. See what is happening. If you see some 25 years back, we didn't have many car manufacturers in the Indian market. We had only Fiat and Ambassador. And later it is joined by the Maruti. So we had hardly 2 or 3 people, and then you can think of it. Suppose they were expecting a volume of 100,000 or maybe 1 lakh car to be sold. So they can always divide the development cost of these cars by 1 lakh, and that would be the cost they can put on a car which they have developed. But what is happening today? We have so many players. So what had happened is, though the market has increased, but if you calculate the model sold, the volume sold in the earlier and volume sold today per model is reduced. Not only that, earlier there used to be change in the model maybe after 5 years or 7 years. Nowadays, after every 2 years or 3, they talk of phase shift, they talk of including some innovative things into this. So finally, what is happening? Because of the less sale of that particular model or less volume per product, the development cost has gone up. Now, once this development has gone up, this is a matter of challenge, because this will definitely going to increase the cost, because manufacturing cost is not there. But how to reduce the development cost is one of the issues people have to think of. Second is people are coming with many new materials, new technology, new words, and they're using whatever the resource they have, and they're making the things compatible for the adverse duty conditions. And that is also one of the challenge. And what is happening altogether, a fast changing technology is coming. For example, now people are talking of the smart cars. People talk of intelligent system for the engines. So these things which is changing all around the stuff. So this is a matter of concern, and today industries are challenged differently. If we talk of the product wise, earlier the number of variants were less. For example, if we talk of a single car, even in some particular model itself, now we are talking of VX, VXI or LX, LXI, so many particular variant in that. It is increasing because people are trying to give more and more features and attractive cost. They're trying to make the balance of it. So more and more variants are coming. Now the product lifetime is reducing because what is happening after 10 years or earlier there used to be change of the models or altogether after 10 years or so. But now after every 2 years or 3, there is a phase shift. You have to come up with something new, change the stuff, then only you can sell into the market. So this is going down and down. And in terms of the complexity, it is going up, and delivery, people want immediately, they cannot wait. So this is the trend in the market. So people have to work for immediate delivery of the best quality product with maximum possible feature at the lowest price. So this is again, you cannot think of a immediate delivery of the best quality product with maximum feature at the lowest price. So what has to be done? What thing can be done is people can work on different methods, try to understand, and in some way, additive manufacturing can help in this. See, you take a conventional manufacturing process, we start with the synthesis, we go for the analysis, we go for the documentation drawing, we do the planning, we procure the raw material, we go the tool procurement and CNC manufacturing, and we go for the quality check, packing, and use. So this is the conventional manufacturing cycle. Now, if we talk of the additive manufacturing, some of the stages are not required to be attained. For example, documentation and drawing. Yeah, you need not to, because you have a 3D model, you need not to make specifically drawing and documentation to do the job. So you need not to worry. In terms of planning, now many of the planning are done with the CNC machines or the software that the 3D printers have. So you need not to do a lot of planning. So that is reduced. In terms of raw material procurement, I am talking of the timeline. You cannot buy right away. What is happening earlier today when we talk of this, when we talk of the procuring of the raw material in the conventional design, what you have to do first, you have to design or define then only you can procure the size, procure the stock to fabricate the component. But what is happening in additive manufacturing, since we are using a shapeless material like wire spools or maybe borders, you can buy in the bulk and keep in the stock. The final design of the component is now not that much needed as it is needed in the conventional method. That is there. Now, you need not to worry too much about the tool procurement. So these are the, some of the things that is a lot of gain with the additive manufacturing which is happening. If we talk of Indian perspective, Government of India is doing a great job, coming with the different ideas, trying to push the things to the next level. And they have identified different areas for the disruptive technology, especially Niti Aayog. They have identified as a smart manufacturing one of the area. And they are doing it. And they are pushing this. They are generating the awareness among the people, trying to bring this new technology, new area. So now issue is, what are the advantage, limitation, and sustainability of additive manufacturing? For example, the advantage is complexity for free, you need not to worry. See, what I want to say is, when you convert a 3D product and slice it, the 2D slice is very simple and it's not difficult to make. But when their slices are put one over another, then it becomes difficult to work on. So what I want to say is, complexity is free is one of the buzz line people do as an advantage of additive manufacturing. Second part is simplification of part fixing. Most of the process, they do not have direct contact of the job and the deposition head, right? So as a result, like you see in case of subtractive machining, there would be some, there's a cutting process. And there will be lot of cutting forces, and it is not required in additive manufacturing. Since it's not there, there is simplification of part fixturing. In terms of mass customization, you can think of doing it. You can customize a product because you're making one by one. There is opportunity you can customize and do the things in different way. Another very nice concept that we are talking today is integrated components. This is altogether different and newer stuff. For example, you can think of making a pre-assembled component which was not possible. For example, we all know that one of the common mechanical engineering component is the bearing. So bearing has got 4 parts. One is inner shell, inner race, outer race, or some balls or rollers, and cage. So these are the 4 parts. Now issue is, can you make these 4 parts in single go? People are trying to develop it. And once this is done, this will be really beautiful. That whole bearing is built in there. People have already tried with the plastics. Polymers they have done, but they are trying to do it in the metals. Still, metal is far from getting it done, but one day it will come. Moreover, if you want to have a component in which you want to have some electronics embedded, which is possible now, which was not the case earlier. There are many examples. See, one of the example is in our ISRO program at the rocket injectors. They wanted to see what is the temperature during the flight. Now, what was happening earlier, if they put some sensors, these sensors will take some space and it is very difficult to make them in. And it is also putting some retarding action over there to the work. So what they did is, they thought of, can this component be integrated in the rocket nozzle itself? So some of the things are tried and they did it, and it's really great job and very good understanding about it. So this is the thing which is happening. Another advantage of additive manufacturing is material design freedom. When I talk of the material design freedom, means you use the material when and where it is needed. For example, if you want to have high conductive material, it's better to have a copper-like material. In this pandemic, when we talk of bacterial or antiviral properties, then copper and silver are the best. But copper and silver coating everywhere is difficult in different shape. One of the way can be, you can use these things in right away in the different coating, and you can deposit it locally, which is more in contact. So that sort of thing is possible. So that is the material design freedom you have. You can have different material at different locations. That the way thing can be planned. The 6th is logistic freedom. In logistic freedom, what we do is we can design here or take the advice of anybody across the globe, and you can think of getting it fabricated at some other location, because simple file transfer is taking place, which can be done in few hours. Because I'm talking of loading and downloading time with the very slow line connections. So that is there, and logistic freedom is working on. Reduce wastage. You can think like you can do very nice arrangement, and you can plan the project so that the wastage is least. With so many good things, what are the limitations of additive manufacturing? One of the limitation is its costs are high as on today. At the time, many new processes will come, new entrepreneurs will come. We are expecting this price to go down. Mechanical properties, especially in the metals and the ceramics, it's an issue now. People are working on it, how to fix it, but it will take some time, and things will be improved and done. Still, there is a need of post-processing. I told you to remove the support structures or some finishing operations. It can be resolved later. Built volume. So built volume is another issue that we have to work on. Today it is a limitation. The size of the machines are maybe 300 by 300, 500 by 500. So people are thinking, can this be increased to make the large? This is one of the limitations. Another part, since we are using layer by layer, if you have a design model like this, then you join them and try to make it. So this is the issue. We can have lower thickness. Lower thickness is that the fabrication time is higher and stress stripping is there. So we have to really compromise on these. But again, still, the process like this is difficult to make. After that, the question is additive manufacturing sustainable? This is a big question. Sustainability issue started somewhere in 1972. People started working on this. If I see in terms of additive manufacturing says that the raw materials are reduced, the requirement is reduced, energy, waste generation, and pollution is less because you're using with a limited material. Functionality and operation efficiency is increasing, and overall carbon footprint reduced. Moreover, it also allows a decentralization of manufacturing, which ultimately allows the sustainability. So these are the parameters which are pushing the things to sustainability of additive manufacturing. The classification of AM. The additive manufacturing can be classified into 7 as per ASTM. ASTM, I told you already the name, ISTM 52900. It has classified additive manufacturing into 7 classes. One is hot polymerization, powder bed fusion, material extrusion, material jetting, binder jetting, direct energy deposition, and sheet laminations. So these are the industries which are, these are the ASTM standard, and these are the name with the industries knowing this process. And these are the different vendors, those who are supplying these machines. Let me start one by one. The first is wet photopolymerization. This was the first process to come in, and a lot of things are done. Now we have 2 versions of wet polymerization. See what happens in wet polymerization. I'll just brief you. Many of you must be knowing, but still a quick review and quick revision. See what happens in this. We have a chamber. In this, the photopolymer is put. The laser comes, the scans, and melt and deposit selectively the material. It converts this monomer into into polymer by exposing this by using selective laser. So what is happening? Based on the geometry of this, the combination of Z and this scanner is made, and whole component is given to the shape. So this is the. So now if we talk of this concept, now there are 2 types of machine available. One is called top-down system, another is bottom-up system. In top-down system, what is happening? From top, you are building and pushing the platform down and down. This is the top-down system. While another system which is also now available is called bottom-up. In this, what is happening? The laser is here, scanner is here, and everything is pushed from the bottom, and it is going up. They have one transparent window, and the basic advantage of these two, if you compare these two processes, you'll find that in top-down systems, you have to have this whole thing filled with the resin, and then only you can build. But in this particular case, a very small layer of this, maybe if you want to have a layer thickness of say 100 micron, even if 1 millimeter layer thickness over here is enough to get the things uniformly deposited. So that is the advantage of this approach. The less resin is used, less resin is required for doing the job. So this is a more popular system in this. Now, if you compare the advantage of this is simple and compact. Quality and accuracy is good. Multi capability is fine. Multi-material capability is possible. For example, you can go up to N with the material 1, and after layer N, you can change the resin and you can start another. So multi-material capability is possible. It is mostly used for the prototyping. In terms of limitation, it's a costly process. It requires post curing. It requires support structures and material limit. These are the limitations. These are commonly used for patient-specific model and functional parts, implantable device, and tissue engineering. In some of the cases, people trying to use for the tooling application and microfluidics. Another method of the using is the material jetting. In material jetting, what is happening? As the name suggests, there would be a jet, and this jet will be falling on the component, giving shape to it. So in this particular, 2 sort of approach are used. One is continuous jetting, another drop and down demand. So what is happening in continuous jet? There would be ink filled in details, and you are pushing it, and then this is falling continuously down and down. And what are we doing? This is the surface where you want to print. There is a field, and this particular field plates pulls this and allow the falling disk. And when this field plate doesn't push this, then this directly falls into the catcher, and that's the way continuous jetting happens in the material jetting process. Another approach people use is the drop on demand, and this what is happening, the ink reservoir is there, it's fall here, and then whenever the head goes to the location and when it sees that there is to be deposition, then it drops the defined volume of the drop. So that is the defined volume of the ink in form of drop. So drop on demand, these are the two processes which are used. So in this whole process, what is happening? There would be a building platform, there would be build material, it will be falling on it and getting certified. This way, the things goes on building in the material jetting process. There are many variants I show you. I already discussed the ballistic particle manufacturing, aerosol jet technology, or laser induced forward transfer. These are some of the variants of the material jetting. The advantage is its accuracy in finish is good. Full color and multi-part are possible. Removable support material can be done. In this particular case, since you are using jet, people have come with the idea like, for example, they can use some, soluble, water soluble or some acid soluble support structures. So what you're doing, you're putting the component into this, all support structure goes. So very simple to move it and work on it. That's one of the advantage. In terms of the limitation, the mechanical properties are poor. The process is very slow. Materials are limited because the material should be, you should be able to give the shape to it. You should be able to pull with the charge. So there are limitations. And these are basically used for, specifically used, they are in automotive, medical, jewelry, and electronics. One of the very common uses the material extrusion. You can see, we all know that about the FDM. I will not go to the very much detail of this. These are very common. And today I will say that if you go to the FDM market, the printers are available from maybe 15,000 to maybe few lakhs. Now, as an entrepreneur or the institute which want to work on it, it's very simple to do it by yourself machines, maybe 15,000 or 16,000 or 20,000 to start with. But reality is these machines have got some interesting problem. For some components, few number of these things, they work well. But if you want to really have an engineering component, better design, then really you have to go for a more precise and machine with the right parts and material. This is also advantage of this process is its low cost, simplicity, and safety is there. Material wastage is not there. So many materials are available in the market. Material change is easy. Just pull on the filament and it can be changed. The limitation of material extrusion is surface finish and accuracy, build speed, anisotropy, and support materials. These are very good. Typical application is concept model and functional testing, aerospace, medical, and tooling. So these are the applications that people are working on it. Another concept is binder jetting. This is one of the things which is now more popular. HP has recently come up with a machine, and now for the metals, and people are using and buying it, and it's a hotcake in the market. So in this process, what happens is there would be a material which will lay this by the leveling viewer, and there would be some, I'm using the word inkjet print head. So this will be feeding some binder material. This binder will be, falling drop by drop and getting the material joined by bonded together. So that is the concept. And this machine, you must be knowing the HP were good in printing technology. They were able to feed very nice color printers, laser printers, even the desktop printers. So something similar technology they have employed here. And in this, what is happening? The binder is put into this, and there would be there would be one metal or some ceramic layer, and this binder is joining these ceramic and the metals. As a result, the component gets solidified. So this has come up very nicely, one of the hot cakes in the market. This doesn't need support structure, economic supporting here. Warping is not there because there's no heating. Current part can be made. You can use different ceramics, different inks to do that. Build rate is high because you can use multiple head and do the job. You can have 10 nozzle or 20 nozzles working together, and doing the job. So it is possible here. Build volume is not a limitation. You can have just structure, mount other things on it, and works on it. And it is since distortion is less, build rate is high, warping is not there, support structure is not there. This is now very good for pre-assembled components. So that is the thing which is being seen as advantage. The limitation is low part strength, need of post-processing, shrinkage is the issues. And application is like color prototype, decorative art, metallic component, people think of tooling, biomedical, fiction, electronics. So these are the applications. So the other process is sheet lamination. In sheet lamination, LOM was one of the things which was very popular, laminate object oriented. In this, what is happening? We'll be pulling a layer of the sheet. This should be sticked, and then it will be cut and given the shape. So this is the process, very simple. The advantage is there is no thermal stress. Integrated component can be made. Color part painted material properties are possible. Separate support structures are not required. Cost is low. The disadvantage is the resolution is low. Hollow part cannot be made. Material wastage is there because you are taking a sheet and cutting it. It involves a sort of material removal. So that is again a problem over there. But this is very good for the microfluidic devices, tooling, prototyping, visualization, and smart structure because heating is not there. So this is the thing. The sixth process is powder bed fusion. So powder bed fusion, what is happening? We are having a powder, and this powder is leveled, spread over it with the help of the laser. This is melted and deposited. This is the process. So now the laser, it can be used either laser or electron beam, but finally metal is melted and done. So this is one of the thing which is more popular in the country. There are many manufacturers, for example, SLM, EOS, Renishaw. They are sending a powder bed machine here. This is the machine that we built at RRCAT. This is a laser additive manufacturing based powder bed on powder bed fusion. So you can see it uses 500-watt laser, and then we have a Calno scanner, then a pre-built plate. So spreads the powder, deposit in shapes, and we have made many shapes. You can see how the machine works in open-ended. You see the powder layer is spread. Now laser will be falling on it, and then melting and depositing. So then we are laying the another layer. So another layer is laid on this, and so what happens is, when after deposition, this build plate goes down by predefined volume, predefined height. After that, we deposit. So that is the way it works. The present capacity of this machine is 250 by 250 by 250 millimeter. And we can work from 0.02 to 10 meter per second. We have worked with many metals in Cornell as these things are going. Now, this is very good. It can work with various shape complexities. Thin features can be given. Mechanical strength is pretty good. Dimensional accuracy and surface finish is possible. Powder can be used. But the limitations are limited material capability. Now, just a few days back, I was going through the literature. I found that the people are trying to develop some multi-material capability in powder bed fusion, but still it's working on it. It will take some time to come to that level. Another limitation, it has got a porosity is the issues, because people say that in case of powder bed fusion, you cannot achieve more than 98.5% density. So you have to go for some post-processing like hipping or any other process in this. Build rate is slow, volume is limited, but this is convincingly used in aerospace, tooling, medical, and automotive applications. The seventh process is direct energy deposition. In the last process, what we were doing is we were spreading the powder and then we are sending the laser beam and melting it down. Now, another approach can be you can send the powder, in the form of a stream through a nozzle and feed and in situ melt the material. That is another approach people can try nowadays. So this is a direct energy deposition that is called. So in this, this is system, you can think of a laser, and then there would be a laser beam is coming here, and then you can have a powder feeding mechanism. So the powder will also be coming here. So both will be coming coaxially, and as a result, a laser will melt the metal powders and it will get deposited. For example, you can have a coaxial nozzle. So laser beam will be from the center. There will be 3 stream which is coming falling here. When these people joins together, the powders are coming, laser beam is coming, it melts and deposits. We also try to develop one coaxial wire feeding system, and then it's working fine. In this, whatever laser beam is coming, it is split into 3 beam, then wire is coming here, and that works. This is a machine that we built at RRCAT using in the directed energy depositions. So these machines are being used for making different component shape. We also here in this particular machine, the volume is 250 by 250 by 250, but this cannot be used for realizing the larger volume. So we made another machine. Its volume is 1.6 meter diameter and 1.4 meter length. So this is the component size which can be made into this. It has got a robo head is mounted over it. You can do the shape to the component. The application of direct energy deposition as the good deposition rate, dense and strong multi-material parts possible, larger parts can be made, easy material change is possible. Limitation is dimensional accuracy as compared to powder bed fusion, it's less. Support structure is the issue here. We are able to really work on it as a designer to resolve the support structure issues. Since the high energy is involved, there is a distortion. Typical application is near-net shaping of the parts, tooling, biomedical, cladding of high performance material, and the repair. So after giving you such an introduction, now I'll be focusing on our experience on laser additive manufacturing, what are things we did in the past, and how laser additive manufacturing brought a change in the workflow in our system. One of the very first example is making a columnar bush. This is the first assignment we took up, maybe some 6 years back. See what is happening. These are the bushes which are made up of columni. These are the part of the fast breeder reactor, and these are used in control rod. It is used in control rod drive mechanisms and control rod mechanism. And idea is that there would be a shaft going through these bushes, and your control rod will be hanging on this. That is on the shaft. That is the way it is done in the reactor. Now, what happens is since the reactor is in high temperature and the vacuum, with the time, this ordinary material gets welded with the shaft. And since the part of the control rod, you cannot do this. You don't want this to happen, because the moment you want to control the reactor and you want to push the control rod down, and if it doesn't go down, you can understand what will happen. So what is happening? They want to avoid such a problem, which is called galling. So galling, to avoid the galling problem, they use some special materials. And columna is one of the materials. It's a very hard material in very limited quantity and very costly material. So what they were doing is, to make such bushes, they were taking a stainless steel substrate. We used to deposit the columni using GTW, gas tungsten arc welding, and after that used to machine in and out to get this shape. So that was it. But what is happening in GTW, since the heat input was very high, so the columni was not only limited to this, but it was also getting inside the stainless steel. So there was a dilution zone. So when they were making the bushes, they were to remove even the dilution zone, because they want a pure columni to be there. As a result, it used to take 45 days. And when it came to fabricate using additive manufacturing, so when we started making it, simply we made helical upward motion, and we have some shape like this. After we machine it, and it reduced to 72 hours. So this is one of the success stories. Another point is we try to make low-cost tools. You see, when we talk of the large diameter tools, we are using some cemented carbide or sinter carbide tips. But in small diameter tool, we are not able to do it, because how to mount this, how to tie these inserts, into this tool. So this is one of the limitation. But what we can do is, for the small diameter tool, you can always deposit tungsten carbide using additive manufacturing and then ship it over there. So this will definitely, result in a very low cost tool, because you are not using tungsten carbide to build a shank. You all know that in cutting process, shank is not contributing. The contribution comes only from the cutting edges. So that sort of thing is possible, and we try to build it, and we found it the performance of these tools are 80% of the sinter tool, and things are being done. Another one is we try to make some conformal cavity using laser additive manufacturing. See, when you do suppose you design a die, and after that you do some thermal analysis, and you come to a shape, these are the isotherms over there because of some particular. Now, what ideally should be? Ideally should be there should be a line going equidistance to this red line, so that you can have very good efficient cooling. Conventionally, it is not possible because you have to really make linear holes. In additive manufacturing, you can make the conformal cavities, and these are one of the examples we can. And what is happening, such a small change in the design of in the fabrication methodology and the design yield cycle time change in the cycle times in the order of 20%, 15%, like that. So when you have to make thousands of the components using some dies, then it makes a very big difference in this. Another application we try to do is hard facing, and thus we would use some hard superior quality material, and we develop the nozzles, we deposit the material. This is very good when you talk of making some elbows and bends. You want a very high firmness material over there. Another application we worked on it is development of stainless steel titanium graded transition joint. See, titanium and stainless steel are used in fuel reprocessing plants. See, when you have fuel burnt in the reactor, then we have to reprocess it so that whatever the leftover fuel, some of the things can be recovered, and then it can be go for further processing and reusing. So what is happening, since in this process people use boiling nitric acid, especially for the fast reactor spent fuels. So they want the reactor shell to be made up of titanium. I'm talking of reprocessing reactor shell. So the reprocessing reactor shells are made up of titanium because there is a boiling nitric acid there. But what is happening? There are lines where we are connecting the reactor shell, titanium reactor shell. These are normally made up of stainless steel, and reason being because getting everything made up of titanium is very costly. Because it may happen that we may be using for a while only, once or twice for the charging the reactor shell, like that. So titanium is normally not used there. So people are using stainless steel tubes over there and joining it with the titanium shell, and this is the problem. When you're joining titanium and stainless steel, what is happening? These two guys are not friendly, so they don't go together well. Now, problem is when they don't go together well, because metallurgically they are incompatible. So how to make them good? Now, one of the things that we tried is we can always go for a friend. If two people are not talking, and you can always plan to have a third person in between who is friend to both, and that can be the things can be talked. Something similar we tried initially, and we found a bit success on that. Later, we just thought of, in spite of having a steep change in the layer, having a thread in between, why should not we have a buffer layer in the graded form? So as a result, that we tried, and we successfully made the titanium aesthetic design, and it is under testing there. Another application that we try to work is honeycomb shaped orifices. These are again the part of the reactor components. You see, this is very simple to see, but difficult to make because you have so many studs, they have ribs, overhang structures. So baking, and the size is about 75 millimeter, diameter about 3 inches, and the thickness is about ½ inch. So making this is a really tedious task, and there's so many things I've tried. Finally, additive manufacturing we tried, and we have sent it for the testing in the prototype fast breeder reactors. So these are the thing we are doing it. Another concept, we are working with the Bhabha Atomic researchers in development of printed circuit heat exchangers. In this, very fine things are made, especially when you talk of next generation nuclear reactors or supercritical CO2 gas based Breton cycles. What is happening, when this, when you talk of these advanced reactors and CO2 Breton cycles, the cooling circuit that we are using in the heat exchangers, the diameter of size of the tubes are coming up very small. The size can be as small as 2 millimeter or 3 millimeter, and making root of that is also very difficult. So what we did is we try to make a prototype. You can see this is a 1.5 millimeter by 1.5 millimeter square shape, and this is another. So that sort of thing we made at 25 by 25. Another thing we are just building for the real one, 200 by 200 by 200 size. So this will also be tried and done and readily available very soon. As I was discussing with you, functionally graded material of the titanium and stainless steel, you can see in the first layer you can have 100% of B, and as you go up, you can just go on reducing the material B, increase the material A, like that. So once you go on increasing and change the composition of the material as you go, the thermophysical property will also change. So what will happen at the interface, you will not have an abrupt change of the property like this. There would be a graded change. So that's the way it is done, and we try to build it with stainless steel and stellite. And we found that there is a very nice change. You can see in EDS, element dispersive spectroscopy, you can see that iron is coming down like that, and chromium cobalt is growing. So this is the interface. This is the interface. And similarly, if it's talk the micro hardness, this is also changing. Up to here, it's the same. And after there is a change here and this. Conventionally, if you do, then there would be, something like this. And similarly, it will be changing like this. So this slope is possible, and grading has come because of graded materials, and we do it. Similarly, another example, we try to make a graded porous structures. See, when we talk of any engineering design, we had been taught that the porosity is bad. We should avoid porosity everywhere. But reality is, porosity is not bad. Uncontrollable porosity is bad. And what is happening? All these years, since we didn't have control on the porosity, we said porosity is bad. Today, with the additive manufacturing, things are changing. Now we can have a defined volume of the property, porosity, defined volume of the porosity at defined location. It's possible. And you see, we have built a typical structure. You can see 0% porosity here and 60% porosity here, and it's changing. So that sort of is done. You see the microcity images. Here the brown when the porosity is less, and green when the porosity is more. So that sort of thing is possible. You can design the component, make the component of fly, shape of the porosity can be controlled. And in that way, if we can, estimate the things in right, and it is predictable, then these things can be deployed in much better way in all the engineering applications. We have built many shapes and components. You can see we made prototype hip implant, impellers, porous structures, honeycomb gear. You just think of it, a gear of this much size of around 150 millimeter diameter with 40 millimeter ID with honeycomb core. How much time do you think that it is built? And the thickness is, say, 40 millimeter. How much time do you think that it can be built? I can just share with you the time we took to build it is about 4 hours. You cannot build this gear using any conventional method of technology in 4 hours. Because yes, you can say you can do the forging or some other method and you can have a die. But if you talk of the total process time, it will be much larger than that. So this is possible. We did it. If you talk of this impeller, you see such a nice profile has come. This is again built by additive manufacturing. So what I want to say here is key additive manufacturing is joining of material to make the part directly from 3D model, following layer by layer approach that we have already discussed. advantage of additive manufacturing is not to replace the conventional manufacturing process, but it is going to coexist with other existing manufacturing process where we can have a techno-economic advantages, how and where which process has to be applied, so things can be done in better way. Then you know that ISO 52900 has classified into 7 categories, and all the processes has got distinct advantage and disadvantage. I'll already share with you our experience with that. And with this, I close. Session is open for the question answers. Hello. Hello, Mike. We can show you 3D. I can show you. Just hold on. If I have on this laptop, I can share and show to you the 3D clip. Yeah, I'll show you the 3D clip, how the components are built. This is basically full process that we have built, and a lot of things are there.
The evolution of human civilization sees the sudden turns when it strikes with new idea. It changes the world as it was never before. Every new idea brings evolution changes the very face of life. Recently, such a revolution has come to management that changed purpose and our from subscriber to editor. Introducing FDP, hands-on medical manufacturing. A technology that revolutionizes medical hardware, companies design and manufacturing. AI has prepared an advanced technology of hardware designs that human designer estimate medical technology and medical products and translates to products used in functional labs. Experts will
Excuse me, sir. Video is not audible, sir. Sound is not clear, sir. Video.
I'm trying to increase the volume.
Okay. Thank you, sir.
Hello.
Yes, Meg.
Sir, some participants are asking the questions. Can I take?
Yes, please.
Sir, here one participant, that is Madish Kumar. Whether hard implementation is possible through 3D printing? I heard the research is going on.
See, that is true. There is a lot of research, especially in tissue engineering, and a lot of things are being done. Today, making of heart by additive manufacturing is not possible, but yes, research is being done in this direction.
And another question is, can we print ceramic?
Ceramic can be printed. We have already done alumina, Al2O3, and silicon oxide, SiO2. This is possible, yes. But only thing is, it has got a lot of issues. Process window is very small. One has to be very careful. Process condition has to be in very big control way. So that's possible, yeah.
Yeah, thank you, sir. And another question you can ask in chat box. If somebody asks to any question.
Yes, sir.
Yes, yes.
Sir, this is regarding the selection of machines, sir.
Yeah.
If a person want to become entrepreneur based upon this 3D printing, can he become entrepreneur, sir?
See, Mr. Viragari Venkatramana, right?
Yes, sir. Yes, sir.
Yeah, Mr. Venkatramana, this is very nice question, and this such question should be asked in today's atmosphere. See, what is happening? What I say is, whenever we talk of starting a business, because I have a couple of my friends are also in this venture, how should you start in this? The first thing is you can start with a low-cost printer, for example, FDM, material extrusion process. You can start the job, come to the market, start doing it, get some knowledge. The second stage is to go for second printer you can go for is selective laser sintering, and third you have to go for selective stereolithography. So once you achieve these three steps, then fourth will be the metal printers. So what I'll say, that to talk of the cost, the FDM would be costing few thousands to few lakhs. So you can have some medium range printer, buy this, start searching the market. And what I say is, Mr. Venkat, you have to understand in 3D printing, nothing happens in few hours. Nothing happens. Suppose you have a very small component may be the size, say 20 by say 30 by 20, 100 by 100 by say 5 millimeter. This is such a small job. Building any shape into this, giving some complex features on it, may take some few hours, 3 years, 5 years, like that. So one has to work on this. So what I'm saying is, to start a 3D printing, first you should start with a low cost, start generating revenue on it. Once you have some revenue, you have some knowledge about the technology, then slowly you can grow up with the SLA and then SLS and then metal printers. That's the way people are doing, and the way people are working today. Yeah.
Thank you, sir. Sir, one more question, sir.
Yeah.
Actually, my plan is that I want to venture into the medical applications.
Yes.
As you suggested, can I use FDM machine for that application?
FDM can definitely be used. Recently, I know just now I'm in process of writing a chapter for one of the upcoming book, and that we are already writing on how medical devices can be made. I can, the material that people use for FLA is, FDMs are basically PLA and APS. So these are definitely are used and a very good option. But only thing is when we talk of these material and this, there are always issues with the approval from agencies, and that is a tricky. But again, if you are using some component for the exterior, it should not be a problem, and people are able to go around, and some people are doing the business in this direction. There is no issue on that. Do you have some product in your mind, or just like you said you want to start with something in medical?
Yes, sir. Actually, we have a good hospital near my house where it works only on the bone fractures, leg, jaws, and hands fractures. Every day there are 20 to 30 cases that are coming to us, and they need
Right.
that. So I thought venture into that.
Yeah, no, it's a good idea. It's good idea, really good. But then again, you have to see. Means you want to go, you want to replace the conventional casting, with the 3D printed part, right?
Yes, sir.
You have to really see the economic viability of it. Technically, it is viable. Because what is happening if you go for the cast in the market, people may be charging you 500 or 700 for some small cast. But if you go with the 3D printed part, definitely you will not be able to give it into 700 or it would be few thousands, maybe 2000 or 2500.
Okay.
So you have to pitch it. What are the advantage of these particular stuff, and how things can be pushed in right way, and if you can convince people to take up, yeah, it's good idea and a lot of advantages there. But again, issues who will buy this? Definitely, it's a premium segment. Health is a really premium segment. Thing can be tried out, and there is opportunity. FDM can definitely be used for broken legs and limbs. It can be used to make the precasts. It can be done.
Sir, another question, sir. In your presentation right now, you showed that from CT scan image we can get the design.
Yeah.
Should we do any repeating work in that design, or that CT scan image conversion?
Yeah, what I showed you is basically to make a prosthetics which goes inside the body. It is in vivo prosthetics. But when you talk of the precast, you need not to have CT scan. CT scan will be a costly affair. I will say that you can have some scanners, and the scanners can be some handheld scanners of maybe that you can get one market in few lakhs, and then you can scan and see what happens is, Mr. Venkat, if I talk of this medical business, I can tell to you how the thing goes. Suppose somebody meets accident, he comes to the hospital. The first thing the doctor says is they put some kacha plaster, isn't it?
Yes, sir.
Posters. And then on the third day or second day, they put after seeing all the X-rays and all, they put the permanent one. So in the business that you are talking of, you can have a scanner. If the moment some case is reported, immediately you should get imaging done, and you can have the information of the fractured area, and then you can design the precast. And after that, when he comes on the third day for permanent person, you can offer your precast.
Okay.
So that sort of thing that's possible, right? So as far as the fitting the technical wise, that's why I'm taking technical wise, it's viable. But commercially, how viable it will be, how things can be. What my experience has been in this area is, if you buy low cost machine, there would be more number of failure while building the component. And if you buy a relatively high cost machine, your working cost goes up. So commercial viability is the issue, that if you can work out, come up with some nice business plan, technically it is viable. Business plan wise, you have to link on 10 components.
Sir, one last question, sir.
Yeah.
What are the best products that can be produced on FDMs, fusion deposit machine?
FDM basically, what I say is some of my friends are already working in this area. So they have, one of my friend is in Mumbai. He has got 40 machines, FDM machines.
Oh.
And all are working, he has employed a full-time electronic mechanical engineer diploma fellow to repair and fix the machines, So that is sort of scale we are talking, right? So what the volume he has is customized product. And, especially for the, suppose you want to make a huge Ganpati statue in your house, maybe of 3 feet, right? And different, and you want some particular feature. So FDM is one of the options. And only FDM will not work. Only FDM will not work. You need to have many other things on the place. For example, some post processing is required. You need somebody who can do good painting, because when you talk of some sculptures, there would be eyes, nose, and coloring scheme. So you need somebody who has got favor of that. Then another area is how to do the finishing part, because there would be removal of the support structure, sanding, polishing, then surface processing. All these things will be a part of this. So if you see as the industry, when I talk of this person who is running a company with the 40 machines, he is equipped with all these people and able to do the job. So yeah, there is opportunity, and it's a really we can work on it. You can plan to work on these things, but you have to think of you have to guide out, take the people from other area. For example, one of the very creative option is making mini-me's now. Figurine. So the people are posting it, and they are selling in maybe from 3,000 rupees to 10,000 rupees, depending on the size. I think for the 6-inch they charge some 3,000 rupees. 6-inch height of figurine. So you need to have somebody who can extract the information from 2D image to convert into, say, printable model. So I mean to say, you need modular, you need a pre-processor side, you need somebody who can do the post-processing, and alone you cannot do this. So if you have a tie-up, very nice tie-up with this, it can be done. Yeah, it can be done.
Thanks a lot, sir.
Thank you.
So if anyone have another question, can ask. You can also ask in chat box.
I think Naini Pavan Kumar has asked, where is the ceramic 3D printing available in India? See, what is happening, there is a company called X1. Naini, there is a company called X1, EXONE. X1 is, they make, so you can contact them. Machines are available, and very large machines are, very large size machines are available for ceramic printing. We are doing with the lasers, so we have other issues and we are trying to fix it. Yeah, but again, that is for some other applications. Yeah.
Is it X1, sir? X1?
EXONE, X1.
Okay, sir.
The X1 is the company who make the sand molds.
Okay, sir. Thank you, sir.
Yeah.
Okay, this is the last call. If you have any question, you can ask. We have just 5 minutes more.
I think people have understood everything.
Yes, exactly, sir.
So let me close my session. Thank you very much for inviting and giving me opportunity to speak out. I think people really appreciate it, and it was useful for all. And I think good starter for you guys to start with.
Yes. So I want to inform you, all the participants, that your query is regarding biomedical applications, and sir also told about the miniature design and printing. That all I have covered in this FDP only. You will get perfect idea for startup business and practical application of this miniature design printing biomedical application. We have a separate session for it with expert. We have Dr. Y. Modi from JUET Guna. He is expert in biomedical design and printing. and we have also expert from Vadodara, that is three-dimensional lab. We have expert from Indore, Kanika lab. They are actually doing or running their venture for these applications. So I would like to thanks. It's my privilege to give vote of thanks to Paul sir, to you, and I think you have covered all the aspects. How does it help for the people or the society, market size, trends, cutthroat competitions, advantages, classification, application, and other things. So thank you very much, sir, for your kind word and information. It will definitely help of all. Thank you, sir.
Thank you, man. Thank you very much.
Thank you, sir. So we will meet in another session. Will be start from 12:30, in which I, Mayank Gurjar, will tell you about the CAD modeling and file format. That is the step 1 of the 3D printing and design. So I will take this session from 12:30 to 2 p.m. in which I will tell you about the CAD modeling, how it can be done, and after that from 2:30 I will give you a live demo of my printer where we actually print the parts with the PLA and ABS material. So be live in the session and we will meet on 12:30. Thank you. The
Thank you.
attendance we will take from this Google Meet. Do not worry about it.
Thank you very much, sir.
But you have to be there in this Google Meet and be live, because there is some condition for this FDP, Atal FDP, that attendance is mandatory. 80% attendance should be there. After that, you will be eligible for giving the test at the end of this FDP, and then only you will be get certified. Thank you everyone.
Sir, do we get the recording of this session?
Yeah, I will upload all the recordings in a YouTube channel and this link will be shared with you. Don't worry about it.
Okay, sir. Thank you, sir.
Thank you. And all will be joined from this link only.